CIPTA school. So just before we start, I just wanted to just a quick note that the school doesn't end this week. So this is just the first week of a series of 3 weeks of CIPTA school. And we have other speakers in the following weeks, and I hope by the end of this week to be able to announce when the next week is going to happen. So you don't need to re-register. So everything is already been done. So you will receive the keys to access the following lectures in January and February. So the lectures will be recorded and will be sent to all the participants. And also in a couple of months, they will be also accessible, available and accessible from the cipta.org website. So today we have Credal Networks. We have Fabio and Dennis talking about Credal Networks for the opening of the school. Just a quick introduction about Fabio. Fabio Cozman is a full professor at the Escola Politecnica, Universidad de Sao Paulo, and is director of the Center for Artificial Intelligence at USP. His research is in machine learning and is engineer and PhD, has served amongst other duties as program and general chair of the conference on uncertainty in artificial intelligence, chair the International Joint Conference on Artificial Intelligence, associate editor of the Artificial Intelligence Journal, Journal of Artificial Intelligence Research, and Journal of Approximate Reasoning. He chaired the Special Committee on Artificial Intelligence of the Brazilian Computer Society and received prize for scientific merit in artificial intelligence by that society. Dennis Deretani Mawa is assistant professor at the Department of Computer Science of the Institute of Mathematics and Statistics of the University of Sao Paulo. He obtained his PhD from the University of Lugano, his master's and engineering degrees from the University of Sao Paulo. He has authored and co-authored over 50 articles in journals and conference proceedings, and his research focuses on the theory of probabilistic reasoning and its application to artificial intelligence and machine learning. So with that, I welcome our speakers and lecturers of today, and I leave it on to you. Thank you very much.
Okay, thank you. Thanks for the invitation. Thanks for the kind words. I really appreciate. Let me ask if you are listening to me and watching the slides correctly. Is that okay, Marco?
Absolutely. It's yeah. It's. I mean, feel free also to interact and ask questions. I mean, it's not a it's not just a talk. I mean, it can be interactive and anything. So
yeah. Okay, so like I said, it's a pleasure. Thanks for the invitation. Thanks for the organizers. I'll be talking a little bit with my colleague Dennis on Credal networks. This is a family of models. This is a formalism to represent certainty and to reason about uncertainty. We'll be talking about the specification of Credal networks, a little bit about what they are, how they can be built, and we'll be talking about algorithms and complexity of algorithms. So there will be basically two halves. First, we will be discussing basic concepts, starting from Credal sets, just basic stuff. If you know about Credal sets, we'll be spending maybe 5-10 minutes repeating things you know about. If you don't know about Credal sets, so this will be sort of a gentle introduction, and we'll be discussing Credal networks, their extensions, and one particular inference is called marginal inference. That is quite important. And then in the second half, Dennis basically will talk about more advanced topics. algorithms for marginal inference and other sorts of inference like decision making. We'll be talking, Dennis will be talking about eliciting, building, learning from data, and actually applying Credal networks. Okay? So that's the plan. We'll start with some basic concepts. And really from the beginning, really start from Credal sets. So let's see what they are and how they behave. Let me start with an example. Okay? So if you go back to a report from the United States intelligence, so it's a report from 1951. It's a report called United States National Intelligence Estimate Report, number 29551. And that report said that an attack on Yugoslavia in 1951 should be considered a serious possibility. Okay, and now then the authors of this report tried to translate that sentence into numbers. And what they came up with was that the odds for an attack ranged from 20 to 80 to 80 to 20 in favor of an attack. So if you translate odds into probabilities, you see that what they're saying is basically that the probabilities were between 0.2 and 0.8 for an attack. So actually they didn't know very much about this probability. It was quite imprecise, right? So there's nothing sharp about this assessment. And so this is basically the idea behind the Credal set. So it's a set of possible distributions, a possible probability distributions, okay? So to get to the right language, let me review a few things. It's just to fix vocabulary. I believe all of you know about probability at some level. So just to fix vocabulary, we'll be using here a space of possible states, a sample space or a possibility space, if you like. And everything is finite here. So basically, there's a finite number of states. And given that there's a finite number of states, all the random variables have finite numbers of values, and events have finite numbers, are finite subsets of the possibility space, and so on. So keep in mind, everything is finite so as to keep matters as simple as possible. So we have a possibility space, and then we have subsets of this space. Each subset is an event. Okay, a random variable is just a function from elements, states, elements of omega, elements of the possibility space to real numbers. Okay, and we'll write the expectation of random variable x as e of x with a subscript p, meaning that this expectation was calculated with respect to a probability distribution p. A probability measure p, if you like. And then we will write p of a to mean the probability of an event A. We will use the usual definitions of conditional expectations and conditional probabilities from standard probability theory. We just write E sub P of X given B and P of A given B. Okay? So this is just to get the notation right. So given this, what is a Credal set? The Credal set is a set of probability measures, okay, that you get when you have assessments. Like you say, well, the probability of an attack is between 0.2 and 0.8. This is an assessment. This gives you bounds. It gives you inequalities. It limits the number of possible probability values, the number of probability relationships. And so the set of all possible measures that you can get satisfying those assessments is called the Credal set. Okay, so usually a Credal set is a set of probability measures on a common algebra. So you have an algebra, a set of events, and then you have a Credal set that is a set of distributions on that algebra. Let me give you an example so that what I mean by an assessment and how you build a Credal set, just collecting assessments. So here's an example where you have 3 states. So the possibility space contains little omega 1, little omega 2, little omega 3. And so I'll write P of omega sub I as P sub I. Okay? And suppose someone gave you a few restrictions, a few assessments. Someone told you, well, P sub 1 is larger or equal P sub 3, 2 times P sub 1 is larger or equal to P sub 2, and so on. So there are several assessments, several constraints here on this line that I just highlighted in blue. So these assessments will produce a set of possible distributions. What do I mean by this? I mean that to define a probability measure on this space, you just need 3 numbers. You need P1, P2, and P3, meaning that P1 is the probability of state omega 1, P2 is the probability of state omega 2, and P3 is the probability of state omega 3. Okay, you just need a triple. With a triple, you define a probability measure on this simple space. Okay, the space of this possibility space with 3 states. Now, these numbers must add up to 1 for this to be a probability measure, and they must be larger or equal than 0. So actually, the set of possible numbers belongs to a triangle. Okay, and if I were to draw this, you would see the figure at the left. And so let me write down here the assessments that I'm talking about. So it's P1 larger or equal than P2 or P3. And then 2 times P1 is larger than P2. And then P1 is smaller than 2/3. And P3 belongs to 1/6, 1/3. And I will just unshare the screen a little bit so that I can discuss the example with you, okay? So basically, if I were to consider the set of all possible triples, P1, P2, P3, this set would be a triangle in a 3-dimensional space, right? So this is the space where each point is P1, P2, and P3. If I have a point here, it's a triple, and it's a candidate probability measure. The probability measures are those points that are larger or equal than 0. Each one of the elements is larger or equal than 0, and the elements add up to 1. So it's actually a triangle like this. Right, so this triangle collects the set of all triples that can be probability measures, right? Now, in this triangle, I can draw these constraints. So for example, if I take the simplest one, P3 is between 1/6 and 1/3. Something like this. Okay, so P3 is in this region. So if I consider planes here, I will reach constraints in this triangle like this. These 2 constraints are representing, these 2 lines, dotted lines, are representing that constraint. And then, for example, I have the constraint that P of 1 is smaller or equal than 2/3. So it's something like this, 2/3 here. And this will give me a cut that will probably be something like this. And if I keep drawing these constraints in this triangle, I will reach a set of triples that satisfy all the constraints. This set is the Credal set, okay, corresponding to these assessments. And if I actually look at this triangle from above, what I will see is just a triangle And this is what you see here in the in my slide. So let me go back to the slide. I hope we can see it now. So basically, at the right, you see the drawing I have here in the screen, in my screen, and then at the left, and the right, you have the constraints, and then you have the Credal set. That is the smaller set, with all the triples that satisfies the assessments. Okay, so this is a Credal set. All right, so let's go ahead. So what can you say about Credal sets? Well, first of all, let's have some terminology, some notation. When I have a random variable, I will denote the Credal set containing the probability distribution for that random variable by k of x. This is a notation by Jerome and Rios, appeared in a paper in 1980, which is probably the first, one of the very first papers that took Credal sets seriously within statistics, trying to get justification and axioms for Credal sets. There were papers before them, but they did quite an extended, detailed job. So Jerome and Rios had this notation. Makes sense to adopt. Other people have different notations, like Peter Wally, he uses n for Credal sets. Okay, so there are different ways to denote Credal sets. Given a Credal set, so if you have a Credal set, if you have a set of distributions, a set like the one I was drawing, then if you take all the measures in the Credal set, and for each measure, you compute the expected value of a random variable, you have a set of possible expected values. And if you take the infimum of that set, you have the lower expectation, which is denoted by underline E of x. And now if you take all possible expected values, okay, and you take the supremum, that's the upper expected value. And likewise, if you have a Credal set, you have a set of distributions, and then you compute the probability of an event A. For each one of these measures, you have a set of possible probability values, and then if you take the infimum, it's the lower probability, and if you take the supremum, it's this upper probability. So these are the values that you see here, okay? And then one thing that often happens is that people assume that Credal sets are convex and closed. Okay, so if you go back to the example that we had before, you will see that this Credal set that is drawn here is convex and it's closed. So all the constraints are impose closed boundaries. This is the usual scenario. Okay, it's not hard to imagine examples where you have non-convex Credal sets, just you have different assessments, the more complicated assessment, more complicated constraints. It's not difficult to imagine examples where you have open Credal sets, but most of the time when people say Credal set, what they really mean is a closed convex set of probability measures. Okay, and when you have a closed convex set of probability measures, things get easier. Okay, because if you, for example, if you compute the set of all possible expected values, it's an interval. It's a closed and continuous interval. Now, another thing that happens is that when you have a closed convex Credal set with finite number of vertices, any expected value any lower expected value that you compute, and any upper expected value that you compute will be attained by some distribution that lies in a vertex of this Credal set. Okay, so when you have a closed convex Credal set with a finite number of vertices, well, that's a good thing, because then you can, if you are interested in computing lower and upper expectations, lower and upper probabilities, you can restrict yourself to just looking at the vertices. Okay, and there's more. So one thing that is really powerful is that the behavior of a convex closed Credal set is completely characterized by the lower expectations, the lower expected values that you compute from it. What do I mean by this? I mean that given a closed convex Credal set, then there's a unique function that maps every random variable to a lower expectation. And if conversely, you give me the lower expectations of all random variables, there's only one Credal set that corresponds to those. There's only one largest Credal set that corresponds to those lower expectations. So it's one-to-one in a sense. Right? So if you give me a function that is a lower expectation, for each random variable gives me a number, the lower expected value, that's the same thing as giving me the largest closed convex Credal set that satisfies all assessments, all lower expectations. All right, so one more thing about Credal sets. So we have to define independence of x and y, okay? Any random variables x and y. There are several ways to define independence. This complicates a bit the theory, because when you look at probability theory, standard probability theory, there's only one way to define independence of x and y. There are several possible ways to write the concept, but there's only one concept. Basically, it means independence, stochastic independence of x and y means that the joint density of x and y factorizes, is the product of the marginal density of y, x times the marginal density of y, or as we are in a finite domain, it just means that the probability of any pair x and y, any value of the pair x and y, is the product of the value x times the probability of the value x times the probability of the value y. Right? So this is the usual, I'm just repeating the usual definition of independence. Okay, so what can happen if you have, what are the possibilities if you have a Credal set? Well, one possibility is that every element of this Credal set, so you have a set of distribution. So it might happen that every element of this Credal set satisfies stochastic independence of x and y. So that would be super super great, because then, I mean, they are independent. They are element-wise independent. And this is what's sometimes called complete independence of x and y. Now, the problem with complete independence is that this constraint usually leads to a non-convex Credal set. So only a non-convex Credal set can in general satisfy the constraint that every element of the set factorizes to satisfy stochastic independence. So if you are really committed to convexity, if for you every Credal set must be convex, then complete independence does not work for you. Okay, it does not work, because complete independence may lead to non-convex Credal sets. So there are two other concepts that are used. There are other concepts, but in the interest of trying to be as simple as possible here, I will focus on two other definitions of independence. One of them is called strong independence. Now, what is a strong independence? A strong independence is basically complete independence, but with convexity, right? So it's like you really like convexity to the point that you adopt complete independence, but then you convexify it in a sense. So a strong independence is obtained when x and y are specified with respect to a Credal set, k of x and y, and this Credal set is the convex whole. It's a convex Credal set, it's a convex whole of a convex of another set of distributions, a Credal set that is made fail to be convex. But in this inner Credal set, X and Y are completely independent. So it's like, well, okay, you have a Credal set where they are completely independent, element-wise independent, but then you take the convex hull, okay? And if the Credal set of X and Y can be built in this way, they are strongly independent. So this is actually as close as you can get to the usual stochastic independence while retaining convexity, right? Because if you go with complete independence, which is the first concept, you cannot retain independence. But if you go with strong independence, then every Credal set can be assumed to be convex. So if you like convexity, that's the way to go. Now there are other ways, other possible definitions of irrelevance, independence. Let me give you another one that has led to quite substantial work on Credal networks, which is epistemic independence. But instead of defining epistemic independence, I will define epistemic irrelevance, which is the simpler concept. So we say that Y is epistemically irrelevant to X if for any function of X, okay, the lower expectation of this function given Y is just the same as the lower expectation of the function unconditional, okay? Now, what this constraint means is that the Credal set of X, the Credal set the Credal set containing all probability measures of X given Y is the same as the Credal set for X. Okay, given that, as I said before, there's a 1-1 correspondence between lower expectations and the larger Credal sets that they satisfy. So what this constraint actually says is that everything you know about X given Y is actually the same as everything you know about X unconditional. Okay, so in that, then it makes sense to say Y is irrelevant to X. So this is a concept that is due to Peter Wally. It has been studied quite extensively in the last 30 years. It's not symmetric, so the fact that Y is irrelevant to X does not mean that X is irrelevant to Y. But you can symmetrize. You can say, for example, that X and Y are epistemically independent. If Y is irrelevant to X and X is irrelevant to Y, we could do that. We could do that. I will not do this in this talk, just to make things simpler, as simple as possible. Okay. So actually, in this talk, we'll deal with one concept, basically, strong independence. But we will talk about complete independence and epistemic irrelevance sometimes, okay, a few times.
Fabio, we have a question from Matthias.
Sure.
Matthias asks, can we restrict to just the element-wise stochastic independence of the extreme points?
Yes. Yeah, this is basically strong independence, right? So if you require that you have a Credal set and only the vertices are stochastically independent, and then you may take the convex combinations of all these vertices, you basically have strong independence. I hope that I understood the question. But this definition works for Credal sets that have vertices. So if it's an open Credal set, it doesn't have vertices.
Right. So okay. After taking the convex hull, you might as well just restrict yourself to the extreme points. That was what I was asking.
Yes.
Or do you lose anything by not doing that? By like
you lose when you don't have closed sets, right?
Right.
So
yeah. Okay. Yeah.
If you have open and well, this will get more technical, but look, you can have open Credal sets if you have something called regular conditioning. If you condition on something, the result will may be an open Credal set.
Right.
If you have some kinds of conditioning. So it really is a question. What do you do when you have an open Credal set?
Okay.
Of course, you can assume that all Credal sets are closed, which is fine. And then the definition you just said is clearly enough and probably easier, right? So basically you say, look, if all the vertices are stochastically independent, so it's strongly independent.
Yeah, Daniel is asking a very good question here. I think the answer is no, but I let you answer it. He's asking, wouldn't that be epistemic relevance? The thing I just said, element-wise stochastic independence of extreme points. He's asking whether that's not just the same as epistemic irrelevance.
No, it's not at all. So actually, if you have, so I hope it's clear that when you have when you have stochastic independence of the vertices, the concept is symmetric, right? So if you say X is independent, if you say X is independent of Y, that means Y is independent of X. It's just symmetric by the way you say it, because the stochastic independence is symmetric. But epistemic irrelevance is not symmetric. So it's not the same concept, okay? So saying that Y is irrelevant to X is not the same as X irrelevant to Y, and I think that should be enough to convince you that they are not the same at all, okay? Matthias, was that the question, I suppose?
Yeah, Daniel says thank you. I'm not sure if you see the chat, Fabio.
Yeah, I should see it. Yeah, okay, now I have it.
Fantastic, great.
All right, okay, so I'm taking some time here and now reaching Credal networks. Okay, so if you read the report, that I mentioned, the very first or second slide, the report was not just about attack, was not just about attacking Yugoslavia. It had a more complicated story. So it talked about what could happen in Yugoslavia, what could lead to regime change. It could be an assassination of the then leader Tito. It could be a revolt, a coup. There were many different random variables and many connections between them. So actually, you could easily draw a graph. And what is a graph? A graph is like a structure where you have nodes, and usually the nodes are drawn as little circles or little squares or rectangles. And here we have ellipses, blue ellipses for nodes, and then you have connections between nodes. Here are drawn as edges, okay, arrows. What happens is if you have a graph, the edges, the arrows, can be directed or undirected. In this case, the edges are drawn here as directed arrows. Okay, you can see, meaning that assassination is supposed to influence regime change, and regime change is supposed to influence the decision to invade, and so on and so forth. And now, this particular graph is called then a directed, because the arrows are directed, acyclic graph. It's acyclic because it does not have cycles. Okay. Now, if you look closely, you may think that there are cycles. Because, for example, if you start at decision to invade, you can go to attack and to invasion, and then you might think, well, I can go to build up and back to decision to invade. But when we have a directed graph, we only consider cycles that are directed. Okay, so the cycle that starts a decision to invade, goes to attack, invasion, build up, and back to decision to invade is not a cycle. Okay, it's an undirected cycle, but not a cycle. And so because of that, this graph is a directed acyclic graph. Okay, and it sort of tells the story. It tells the story of the analysis behind this report. Okay, and that is the point of the graph, is to tell a story. Let me give you another story, which is a story you may have heard about. I'm sure Matthias has, but I hope everyone has seen this before. It's like the three prisoners problem. Okay, so you have three prisoners. They are in prison, separate cells. They don't talk to each other. They're waiting execution, and they may be pardoned by the king independently. okay? And they may be pardoned with probability half. Okay, so I'm just drawing here three nodes, because each node means that one of them was executed. And so the random variable E sub 1, E sub 2, and E sub 3 are different random variables that are independent. Okay, and the graph here means, well, they are independent. There's no connection between them. Okay, now there might be a possible event that only one prisoner is executed. This is one possible event. If I want to focus on this event, I may define a random variable K, meaning that the king pardoned in such a way that only one prisoner is to be executed. And this variable depends on the execution of the prisoners. So you have arrows from E sub 1, sub 2, sub 3 to K. Okay. And now one more thing is that the first prisoner, prisoner 1, asks the guard. The guard is honest. The guard will only say the truth. And the prisoner says, well, look, tell me someone about the other two guys. I mean, who's going to be executed? And of course, if you know the story, the guard thinks, well, one of them will be executed. Oh no, so the story is like this. So the guard says, well, I know that only one prisoner is going to be executed. The king has pardoned some of you, and only one will be executed. And so prisoner 1 says, oh, look, tell me about the other prisoners. One of them will be executed. Tell me the name of a prisoner that will be released. One of them will be released. One of them will be maybe executed, but one of them will be released, because only one will be executed. And so the guard says, well, prisoner 2 will be released. And so prisoner 1 computes the probability that he is going to be executed, given that the guard said that prisoner 2 will be released, and then the guard said the only one prisoner is to be executed. So this is like a small graph with all the random variables, and we might attach probabilities to the nodes. Okay, so what can we say? Well, the probability of E1, E2, and E3 is half. The probability of K depends on what the king says, and the probability the guard answers depends on what happens to E2 and E3. Okay. If you know about the three prisoners dilemma, you know that the probability of any prisoner, given what the guard said about prisoner 2 being released and only one prisoner being executed, is just the same as the probability of each prisoner being executed, given that only one will be executed. It's a third. So if you went through this problem before, it's just 1/3. Now, this happens if the probability that the guard chooses to say that 2 will be released, when the guard has an option. So when the guard can say 2 or 3, he will say 2. The probability is half for this decision from the guard. So this is what happens when the guard can decide randomly, I mean, with uniform probabilities. You might think, well, what happens if the guard, you don't know the probability of the guard saying 2 or 3. So then you have imprecision in this probability. So you might then have a Credal network, a network where some of the probabilities attached to nodes are precise. So the probability that E1 is, that the prisoner 1 will be executed is a half, but the probability that the guard will say 2 is not precise. It's not a sharp number. We might even go further in introducing some imprecision. We might say, well, look, the probability that the prisoner will be executed is not just half. We don't know what that is. It lies in an interval, and then you can compute things. And this is what we call an inference. We might compute the probability of E1 being prisoner 1 being executed, given that the guard said that prisoner 2 will be released and only one prisoner will be executed. there will be an interval. Okay, so that's what we understand by inference in this setting. We have a bunch of variables. These variables are associated to probability intervals or Credal sets in general. There are connections between, influences between them, and we are interested in the probability of some random variable, some event, given some other observed events. So that's the main idea. Let me try to formalize a little bit some of the things I just said. And starting from the start. So let me start from some historical facts. So Credal networks have been around for some time. I think the first time they appeared in the literature was some 30 years ago through the work of Serafin Moral and collaborators. They were writing about Credal networks back in 1990. They wanted to basically increase the representational power of Bayesian networks. So that was the idea back then. Since then, around 93, Serafin Moral and collaborators had already message passing algorithms. In 97, Marco Zafalon produced the 2U algorithm. People were writing about epistemic irrelevance already and epistemic extensions. I think we'll get to in a moment. And I think from 99 to 2005, a period when Izipta was beginning and people were really discussing what was the theory behind modeling with Credal sets. The focus went through, moved from probability intervals to more general formalisms like Credal sets, and also a more clear understanding that we actually had several possible concepts of independence. Because like in around 90, people were not very clear about what independence meant. And so there are a few tutorials that you can find in the literature. Some of them go back to that period. Like you can find this tutorial, it's a very interesting one from Cano and Moral. They talk about algorithms already back in 2000, 20 years ago. I wrote a tutorial, a review paper. It's more like a literature review in 2005 for IJAR. This is kind of old, I think, now. More like historical interest, if you like. And then there are some very nice tutorials by Piatti, Antonucci, and Zafalon, and then Antonucci, Campos, Carlos de Campos, and Zafalon. Slightly different tutorials. Like this, the first one, really in red, is really about eliciting, about building Credal networks by asking experts, and it's a very gentle tutorial. The second one in red, this one here, that is a tutorial that appeared in the Imprecise Probability book. Okay, it's very didactic, it's very easy to follow. I really recommend. It's maybe an entry point, a reasonable entry point, if you want to start. It's not really very technical, but it's very nice. And then there are two other tutorials that I could mention. One of them focuses on epistemic irrelevance by Jasper de Bock. This is really very nice. If you want to know about epistemic irrelevance, you should read this. It's very detailed, very, very careful. And then there is another one which Dennis and I produced this year, actually, it appeared this year. It basically contains the content of this presentation, but it's a more technical review. So if you compare this last tutorial with the one by Antonucci, Campos, and Zafalon, maybe this last one, we can say that it's more, it's filled with more technical detail. So it may be less of an entry point, but if you're interested in the question, well, what is actually known about Credal networks, is particularly with strong independence at this point. So this may be a good tutorial to read. Okay. So enough about history. So let's go back to get this going. So like I said before, we have graphs. So each node in a graph is associated with a random variable. We have edges indicating connections between them. This is just like what happens in Bayesian networks. Okay, so let me spend a minute with Bayesian networks. In a Bayesian network, you have a graph like the one I just gave, and then you define a joint distribution over all the variables in the graph. And a Bayesian network is basically a pair. It's a pair consisting of a graph, a directed acyclic graph, and a joint distribution. And what they do is they satisfy jointly a Markov condition. The Markov condition for every Bayesian network is that every variable x is independent of its non-descendants, non-parents. So let me go back to the Markov condition means. It means, for example, that attack here is independent of build-up, propaganda, coup, assassination, regime change. All of those are not descendants of attack, given decision to invade, which is the parent of attack. Okay, so the parents are variables that point to a given variable. So the parent of attack is decision to invade, regime change, are assassination, coup, revolt. Okay, so what the Markov condition says is that given a variable, if you know the parents of the variable, you know everything that you need. You don't need to look beyond the parents. You don't need to look at the non-descendants. Of course, you might look at the descendants, but I mean, why would you look at the descendants? They clearly depend on the variable. But if you know the parents, you don't have to look above. That's the idea. And so if you have a structure like this, or if you have a graph, if the graph satisfies the Markov condition, that means that the associated joint distribution satisfies a factorization. You must factorize like this to satisfy all the independence conditions. It must satisfy in a way that it's the joint distribution is the product of local distributions, a distribution for each node, and for each node what you have is the product of x given the parents of x. Okay, so this is what happens in a Bayesian network. So if you have a graph like the ones we discussed before, like the examples I gave, if you have a graph where each node is a random variable, and you say that the graph satisfies the Markov condition, and you say that you have no probabilistic imprecision, everything is precise, then you're down to a Bayesian network, and it must be the case that the joint distribution factorizes in the way that you see in the slide. Okay, it's just the product for local distributions. Here's an example of a Bayesian network. This was a Bayesian network built in my lab years ago to support medical decisions. Basically, you see that you have nodes. Each node is a random variable. You have connections. You have arrows between them. The node is directed acyclic. And for each variable, you have a single distribution, conditional on the parents of the variable. This is the local distribution. And from this and the Markov condition, you can build the joint distribution for the whole graph. All right. Now, what happens with Credal networks? With Credal networks, is a random variable, just like a Bayesian network. And then you have a joint Credal set, a Credal set containing joint distributions, such that they both satisfy a Markov condition. The Markov condition is the same as before, but it's not as clear as before, because before we only had a single concept of independence. So the Markov condition is, well, every variable x is independent of its non-descendants, non-parent given its parents, like before. right? So if you have a variable, if you know the parents, the value of the parents, you know everything. You don't need to go above. But now the question is, well, what does independence mean? A pair where you have a graph, which is a visual thing, and then you have a Credal set. And they are connected. How are they connected? By this Markov condition. But the Markov condition depends on the concept of independence that you choose. So there are several ways to interpret a Credal network. If you give me a graph, if you give me a bunch of local Credal sets for the variables, I can glue them by a Markov condition that depends on the concept of independence that I choose. Okay? Well, I hope that's clear. So you have the structure, which is the graph, and you have the numbers, which form collectively form the joint Credal set. Normally, what you do is you associate with each node the probability of that variable in the node given its parents. Okay? So let me give you an example. So here is a very simple Credal network, 3 variables. So you have a graph. You see that x is disconnected from y and z. So x is actually independent of x, and x is independent of y and z by the Markov condition, because the x has no parent and all the other variables are known descendants. So x is independent of y and z. And likewise, y is independent of x, and so on. And now I could say a few things about the probabilities of each variable locally. Like I could say the probability of x equal to 1 belongs to this interval. The probability of y equal to 1 belongs to this interval. And note that I always write the probabilities conditional on the parents. Because x has no parent, there's nothing to say. It's just x. Now for z, z has a parent, y. So you have the probability of z given y equal to 1, and z given y equal to 0. Both of them appear. In the left, you have z given y equal to 0, and in the right, you have z given y equal to 1. So what do I have here? I have a graph. Each node has an associated random variable, and I have numbers, the quantification of the Credal network. For each variable, I have Credal sets, local Credal sets, indicating the probability of that variable given its parents. In this case, just one parent. Just when you have z, you have the parent y. Now, because I have this sort of a specification where I focus on local Credal sets one at a time, usually people refer to this as a separately specified Credal network. Separately specified in the sense that for each node, I only give the constraints for the variable in the node given its parents, one at a time. Okay? That's why it's separately specified. I could have a Credal network that is not separately specified. That, for example, I would give assessments, constraints over different variables or over different values of the parents. Just to give you an example, this is possible. So it's not very common to have constraints over different variables or different values of parents of a variable, but it's possible, and people have done it. So there's one structure called qualitative Bayesian network, and usually people say that a qualitative network has a positive additive synergy when it satisfies a constraint like this, which is a weird constraint. I don't think the point here is to justify the constraint. The constraint says that the sum of probabilities for x given events where the parents are equal, the sum of these probabilities is larger than the sum of the probabilities when the parents are different. It's kind of a weird constraint, but don't worry about the constraint. My point is, it's possible to have constraints where you have where you tie values of the parents, different values of the parents, or even different variables, different nodes together. But it's not common. Okay, so I will not spend any time on non-separately specified Credal networks. All networks that we'll deal with in the remainder of this conversation will be like this, will be separately specified, meaning that for each node, you give the local Credal set of the node, given each one of the values of its parents. So I think that here is the quintessential the example that I would like to discuss with you, right? So if you understand this, I think you know what I'm talking about at this point. So if you have a separately specified Credal network, let me go back. So if you have a Credal network like this, a graph, a directed acyclic graph with local Credal sets, what is the joint Credal set that collects all the joint distributions by the constraints in the network? Well, then, okay, now we can go back to the different kinds of independence that we have. So we might have the complete extension. Well, what is the complete extension? It's the largest Credal set where each joint distribution in this Credal set. Remember, so we're talking about a set of distributions, a set of joint distributions. It's a joint Credal set, so to speak. Each element of this Credal set is a joint distribution for all variables in the graph. So suppose we have a direct acyclic graph, we have separately specified local Credal sets, and we are interested in the largest set of joint distributions that satisfy element-wise independence. In other words, each one of the distributions in the set satisfies the Markov condition for stochastic independence. Well, the complete extension, which is the largest such Credal set, is just, well, it's very easy to build. It's basically like you take every possible distribution for each node locally, and then you multiply them all. Okay, and I hope you can get this from this expression here. So it's the set of all distributions that factorize according to the factorization of a Bayesian network with distributions coming from the local Credal sets. So this should be easy, I hope. Basically, the complete extension is like you take every possible local probability distribution and you multiply them all, right? Multiply all possible combinations. Now, what happens here is that this joint Credal set makes a lot of sense. It makes sense because if you have a direct acyclic graph, you have local Credal sets, separately specified local Credal sets, and you look at the element-wise Markov condition, so to speak. You naturally have this set. It makes sense, but the problem is that it's not convex in general. And so here's the problem. So if you are really into convexity, you feel bad about this, right? If you don't care about convexity, if you feel like, okay, fine, I will just take the set. I'll just take the set. So there's no real problem with complete independence, complete extension. But if you're really into convexity, you will feel bad about this because the result joint Credal set is not convex in general. So what you could do then is convexify things. Well, yeah.
Sorry, we have reached the end of the hour. I was just wondering if wondering if we could carry on for 10 or 15 minutes if everybody is okay, and shorten the break a bit.
Yeah, I could have five more minutes maybe. Okay.
Okay, then we have a couple of questions. I mean, if I don't see like strong opinions on the chat that people are against it, I will just carry on. Okay, thanks.
Okay. Well, thank you. Sorry about this. So basically, you could convexify things if you like convexity. So you could take this set of joint distributions, each one of them satisfying the Markov condition for the graph with respect to stochastic independence. And you could take the convex hull of this set of joint distributions. And so this is the strong extension. Okay, this is what we call the strong extension. So here's a theorem. Okay, so let me see if this is easy enough. So if you take a separately specified Credal network, okay, and you form you build all the Bayesian networks, so to speak, from all possible ways to select condition distributions from the local Credal sets. Each one of these Bayesian networks will produce a joint distribution by multiplying its elements, its probabilities. And so you have a set, which is the complete extension. The convex hull of this set is the largest Credal set that satisfies the Mark condition with respect to strong independence. So you have two ways of understanding the strong extension. The strong extension may be understood as, well, okay, fine, I have the complete extension, but it's not convex, so I will convexify. I'll take the convex hull. This is one way of understanding the strong extension. The other way, which is the content of this theorem, is to say, well, look, I'm looking for the largest Credal set, the largest possible extension that satisfies the Markov condition understood with respect to strong independence. In other words, each node in the network is strongly independent of its non-descendant given its parents. That's the Markov condition with respect to strong independence. So if I build this largest set, it is exactly the convex hull of the complete extension. So this is a nice result, okay? And the complete extension is written down here. You can even make things simpler by restricting yourself to extreme points if the convex sets are finitely generated. If they have actually extreme points. Okay, so this is an important result. It means it tells you what it means to use the strong extension. It means that you have a Credal network separately specified, as we are assuming. You're building the complete extension and the convex hull as a means of generating the largest set that satisfies the Markov condition with respect to strong independence. Okay. Well, this is what I just said, and here's some results. I will just skip them. Yeah, so let's go back to our example. Okay, to our simple example. Suppose you have this Credal network here, basically 3 variables in a graph. The Markov condition says very little here. It says that basically x is independent of y and on z, z is independent of x given y, and so on. And then I have these assessments, which are, all of them are local, and all of these is separately specified in the sense that for each variable, I give a Credal set conditional on the value of the parents of the variable. How do I build the strong extension? I take every possible combination of vertices. This is the idea of this theorem here, right? So it's the convex hull of all the products I can build, taking extreme points of the local Credal sets. Okay, so here I have 2 extreme points. Here I have 2 extreme points, and here I have 2 extreme points, and here I have just 1 extreme point. So I can put together 2 times 2 times 2 times 1 extreme point. So I have 8 extreme points for this strong extension. And that's basically the idea of building. So this is for strong independence. Let me just spend 2 minutes and then I'll finish talking about epistemic extensions. What is the epistemic extension? The epistemic extension is the largest Credal set of containing joint distributions that you can build from a graph from local Credal sets, assuming the Markov condition for epistemic irrelevance rather than strong independence. So you take the largest set of joint distributions, such for every variable x, the non-descendant non-parents are epistemic irrelevant. Okay, so the key word is here, epistemic irrelevant. There's a lot about these extensions in Jasper's tutorial survey. It's a very nice paper, I really recommend, but we just have no time to go through the details here, okay? So I think I will just close talking a little, very briefly about the key inference that we have with Credal networks. It's called marginal inference. So marginal inference is just very simple. The idea is simple. It's just to compute the bounds of a variable in a Credal network, given conditional on some observations regarding other variables in the network. So it's to compute bounds on the marginal probability of a value of a query variable, conditional on some evidence on other variables. Okay? So basically, for example, if you have z as the query variable, and you have some evidence y, marginal inference means computing the lower and upper probability of z given y. Okay? There are a few results on them. Basically, I have 3 more slides, but I think I will stop, and then maybe Dennis can start from there. Okay?
Okay, thank you very much. So there are some questions. So if you want to ask a question, just jump in, overtake me, no worries. Some of them in the chat have already been answered. Maybe just post them again.
Yeah, let's see. So I think Danielle had a question. Okay, Danielle, I've already answered. Yeah, I guess Matthias had a question about the assessments. So I suppose Matthias was asking what happens if you have assessments that are non-separately specified to the point where they connect variables not really connected by the arrows in the same structure as they are, right, Matthias?
Yeah, that's right. I mean, you could imagine that you assume your model has kind of is equivalent to a separately specified network, but your assessments themselves might not be separately specified, so to speak. Does that make sense?
Yeah, it makes sense, but I think it's just a theoretical exercise in a sense that I don't think anybody does it, because if you have a graph, if the variables are related in some way, it's natural for you to think about what happens with a variable given its parents. I don't think people actually, I haven't seen any application where people actually give assessments combining variables in different forms of network.
It's very standard. It's a very standard thing to do in applications where, for example, you make a statement about some predictive quantity that is not, unconditionally, or maybe conditionally on some hypothetical data. And that might not be directly related to the model specification. So it's a very standard thing to do in inference.
It actually goes back to the meaning of what it means to have a Credal network or a Bayesian network. Right. Basically, it's natural to think that you will draw the network in such a way that a variable is influenced by the things that actually influence it, right? It wouldn't make much sense for you to say, well, X is here, Y is here. Y is a parent of X, but I have information on X and some other Z, right? So
right, but this does happen. I mean, in Bayesian inference, it's very standard.
yeah.
But
Actually, that's why we're only looking at separately specified networks in
right.
this tutorial. But actually, I mean, it's theoretically possible to have non-separately specified, but I wouldn't bother too much.
Well, I can see that the computations are easier, but I think having the ability of having an equivalent, knowing under which conditions you can make a more general statement in your assessment that still leads to something that's equivalent to a separately specified network would be quite valuable, potentially. I mean, it's just something I was thinking about because, yeah.
Okay.
But thanks for answering. I think you answered the question. So
Sure.
I think Raimundo has a similar question related to computation.
If I may add to the previous question, one way in which I've seen it come to happen is non-separately specified if there's some parameter involved and you specify your model through in a parameterized way. And for example, all the local Credal sets depend on this one parameter. All the local probabilities, I mean, depend on this one parameter. People have a model with some parameter in it, and then they don't know the parameter, and then they think, okay, imprecise probabilities is the same as imprecise parameters, and then you don't have the separately specified stuff.
Yeah.
And this is a way in which it often, people wanting to use it for the first time, typically it happens like that, and then it's stuck at this constraint.
I think Asper. Yeah. Oh, thanks, Asper. Nice seeing you. So so Jasper's right. So it's possible. It's possible to get when you're learning, I guess, right? So when you have some constraints and the constraints on some of the variables imply other constraints. But I think when you're building and thinking about it, so it's usually better to think about separately specified. So let me go. So there are questions here about cycles. So people are wondering whether it's possible to have directed cycles, I suppose. Well, I mean, it doesn't work with cycles. If you have a directed cycle, the Markov condition will not work, because then you have something that is independent of itself, right? So it doesn't make much sense. I suppose you could build a different kind of formalism where things could have cycles. And let me give you an example. In probabilistic programming, there's probabilistic logic programming, which is a different topic. People have graphs that indicate how the rules in a program connect variables. Those graphs can have cycles, and they can have a Credal semantics in a sense. But that's a different thing. It's a different Markov condition. With the Markov condition we have in Bayesian networks and in Credal networks, directed cycles do not make any sense, because then you say, well, this variable is independent of itself, so it does not work. What happens if the variables are continuous? Well, there's quite a lot of work on Bayesian networks with continuous variables. There's work on Credal networks with continuous variables, but not as extensive. You might imagine just having a structure where which variable is continuous, and each one of the local Credal sets consists of a set of continuous distributions. Conceptually, I don't think there's any problem. Computationally, it's more difficult. So I don't think many people have worked with continuous variables in terms of algorithms. I may be wrong on that, but I think it's what happens. I think there's one more question here that we didn't quite get. So it's from Hector. Combinations of probability measures that do not sum up to 1. So I guess when you take the convex rule, maybe I'm wrong in this understanding the question, but the question was, well, combinations of probability measures that do not sum up to 1 are inside the convex rule as well. Well, what happens with Credal sets, Hector, it's not that the probability measures do not add up to 1. what happens is that you have a bunch of probability measures, and the lower probabilities do not add up to 1. Okay? And so the individual probability measures, all of them add up to 1. When you take the convex combinations of them, these are the convex combinations are also probability measures that add up to 1. I hope that was clear.
Okay, yes, thank you.
Okay. Eric is around, so I think no separate. Yeah, okay. So Eric has a point. So Eric is saying non-separately specified Credal sets make perfect sense because the graph specifies constraints in the joint, and then you can specify other constraints in the joint. Yes? Okay, fine. It makes sense in that. So like I said, it's certainly theoretically possible. I don't think, I haven't seen many people using non-separately specified Credal sets because that's not quite the way you think about these models, right? So you put a variable, you put the parents of the variable. These are the guys that influence the variable. If there are other variables that also influence the variable, you will just have them as parents. So that's the way usually you think about these models. But of course, it's possible to have non-separately specified. How would you express a Credal set of distributions of a continuous variable? Well, I mean, I guess you could say, for example, you have a set of Gaussians, and the Gaussians have an interval of variances, and then you take the convex pool. This is actually what Jerome and Rios did in their 1980 paper. They took a set of Gaussian distributions by having an interval of actually expected values and variances. And that gives you a possibly non-convex set, and they took the convex whole. So it's possible to specify, and I'm answering this for Dominique Hose, who asked about how would you specify a set of joint of continuous distributions. Okay, yeah, you could. Yeah, I think that's all, Marco.
There's a question from Alex. Alex, maybe you want to ask that question by voice.
From Alex? Alex Wimbush, right?
I mean, I'll just read it. Cyclic Credal nets should be possible.
It was more just a comment on thinking about cycles in the nets. It wasn't. It was more just like a conversation in chat. Although if it is something that is particularly interesting, we can cover it. But it wasn't a question as such.
Yeah. So you're saying you could have cycles, meaning like temporal evolution, and in that case, the temporal evolution would evolve into stable state, right?
Yeah. That was kind of the intent of what I was.
Yeah. So yeah. So there are Bayesian. So this happens with Bayesian networks. Bayesian networks are all. I mean, they cannot handle cycles by themselves because the market condition would break. It would not make any sense, right? So if you have a cycle, a variable is independent of itself. But if there are some semantics that you can give to a Bayesian network where you interpret these cycles as temporal evolution. So a variable depending on it over time. And there are results on these models. I mean, they are related to causal thinking. If you go back to 93 work by Clark Limor, Peter Spirits, they already had cycles in things that look like Bayesian networks, but what they actually mean is temporal dynamic evolution. And they do look at the stable, the models you get when you stabilize. It's a different model. You could also have the same thing mirrored with Credal networks, but it's a different model.
Okay.
Thanks very much, Fabio, for all your answers.
Sure.
For the chat. So let's take a quick break. We've got 10 minutes. We can move to Gather Town and the lounge. I mean, you can either disconnect or keep being connected here if you switch off the camera, I guess. And then we'll be back in at half past here. Okay, thanks.